Today's speaker is Dr. Kadan Hazzard from Rice University in Houston, Texas. Kadan obtained his Bachelor of Science degree from Ohio State University and his PhD from Cornell after completing his postdoc at MIT, I think. Is that right?
No, Gila in
Oh,
Colorado.
right. Okay. I'm sorry. At NIST, I meant to say, not MIT, NIST.
The other, yeah,
Right?
one of them. Yeah, exactly.
That's it.
Some shared letter.
He completed that in 2000, and in 2014 he joined Rice University in Houston, Texas. Today, as you would have seen in his abstract, Kadan is going to be talking about paraparticles and their statistics. As we all know, in conventional quantum mechanics, in the 3 dimensions, we ordinarily speak of only 2 types of fundamental particles broadly, or 2 types of fundamental statistics, I should say, that are Bose-Einstein statistics and Fermi-Dirac statistics. And these, as we all know from undergraduate quantum mechanics, are the result of symmetry or anti-symmetry of wave functions under, for example, particle exchange, which is in turn related to exchange symmetry under the permutation group. In 2 dimensions, I don't know whether Kadan is going to talk about this, but in 2 dimensions, the permutation group is replaced by the so-called braid group, I think it's called. Is that right, Kadan? The braid group?
Exactly, yeah.
Yeah, and which leads to the theoretical possibility in the case of anyons that they would obey fractional statistics different to conventional bosonic or fermionic behavior. And I think it's true to say that initially, or for quite a while, it was believed that in 3 dimensions and higher, because the braid group simply reduces to the symmetry group, or so it was thought, you might expect to see only bosons and fermions. But as Kadan's going to tell us today, it's not quite as simple as that. And there are interesting things to talk about. So to tell us a lot more about this fascinating area of physics, Kadan's talk today is entitled A Strange Exchange, Paraparticles and Where to Find Them. Thanks, Kadan. Over to you.
Yeah, thank you, David, for the really nice introduction. And I think you more or less have outlined my talk for me. So that's really, I can save some time here. No, it's great to be here. And, short of being in Australia, this is the next best thing. So I'm going to tell you this story about these fairly exotic particles. Interestingly, this is by far the most exotic thing that I've ever worked on in my career. I'm typically working on more maybe prosaic things, very experimentally motivated when we stumbled on this. But we're extremely excited about it. The paper that I'm going to mostly talk about is published just a couple weeks ago here. And I think that there's a lot of exciting stuff. So if there do happen to be people in the audience who are just treading water and just wondering what's the next cool thing to work on, I think there's some brand new stuff here to whet your appetite and maybe get you going on something. And I'm happy to talk more. And again, because this is such a sort of exotic thing, even for me, I'm really going to start from the very beginning and remind us of our sort of undergraduate physics, what are fermions and what are bosons and where do those come from, things like that. So I hope you don't mind, and if you do want me to, make things more advanced or more complicated, I certainly can. But otherwise, just wait, and we'll be sufficiently complicated by the end of the talk, I'm sure. The converse of that is, I know sometimes I think you batch the questions up to the end, but please, I encourage you just to ask a question anytime. I think you can put it in the chat. I'll try to keep an eye on it, and I will make sure that we get to the punchlines that are really important before the end of time, if that's okay with David.
Of course, of course.
Perfect. Okay, then let me go ahead and get started. So the most important things up front, which is just to acknowledge the person who really discovered this idea of paraparticles. So this is Jiwan Wang, a former graduate student of mine, who then went on to the Max Planck Institute and is now headed to the Perimeter Institute as a postdoctoral fellow there. There are many other people in my group working on other things, but the paraparticle was all pioneered by Jiwan. And then I've had a collaboration with an undergraduate student Brown, where Dushan Begus, and he's continued to work on some of these things. There are also some other unpublished things going on by people in the group that I probably should acknowledge, but I didn't have their pictures yet. So, and then I'll tell you a little bit about experimental efforts to actually see these very exotic particles for the first time that are being led by Bryce Gadway, who has now moved from UIUC to Penn State. All right. So let's just jump right in. Before I get into the main message, I did mention that I've worked in several areas, especially AMO physics. And so if you are interested in things like fermions and optical lattices, high symmetry systems, systems of what we call synthetic dimensions, which are very flexible ways of using internal states of atoms or molecules to engineer, say, topological band structures or fun things. We've done a lot of work in these areas, as well as a little bit in quantum information and new architectures. So feel free to send me an email. I'm not going to talk about any of this stuff today. All right, so the main subject of interest is paraparticles today, the only subject of interest. This is also my first time actually giving a seminar or a colloquium on the topic. I've mentioned it in other talks, but this is the first full talk I've given. So this is another reason if you stop and ask questions, it'll be really appreciated. That I love the feedback. So the first order of business before doing any physics is to get some terminology sorted out, because in fact, this word paraparticles resembles or overlaps with other words we've heard. If you've done certain work in 1D systems, especially, you may have heard of something called parafermions. Paraparticles have no relationship to this. So the only reason I'm bringing it up is so that if you are an expert in this and thinking it's parafermions, it's really something completely different. And of course, as was mentioned in the introduction, a lot of us have heard of anyons, which are things that are exotic particles, not fermions and bosons, that have been known now for 40 years, both experimentally and theoretically. But anyons are really restricted to two-dimensional systems. So the whole sort of story I'm going to tell you today is about how you can have particles that are not fermions or bosons even in 3 dimensions. So I'll show you examples in 1 dimension and 2 dimension because they're interesting there too, but the most dramatic sort of novelty is in higher dimensions. But let's take a big step back and just go back to our sort of ordinary situation, the particles that we know and love. Look around the universe, everything we know is a boson or a fermion, right? And we all know that bosons have this symmetric wave function when I interchange 2 particles. They have integer spin. And fermions have a half integer spin in this anti-symmetric wave function, which gives rise to the very different behaviors where bosons, their statistics is that they'd like to clump up, and that fermions are these antisocial creatures that would like to not clump up. They'd like to stay in different states. And so even though there's a rich zoo of particles in the world, they're certainly all boiled down into these 2 types as far as we've ever known. And this is kind of interesting at a fundamental level, if there are exceptions to this, of course, but it's not just at the fundamental level. So particles are really important everywhere. So not just in fundamental physics, but if you're studying a many-body system, if you're studying a material, the first step of writing down almost any theory is to identify what is the particle content in that theory. And so even if you're studying something like lattice vibrations of a solid, the characteristics excitations there, called phonons, your first step is to ask what are those excitations and what are their statistics. And in that case, those vibrations are described by phonons, these waves here. As another example, if you're studying something like a metal or an ultracold Fermi gas, the fermionic excitations, at least if it's in a sort of normal Fermi liquid phase, are fermions. So they're quasi-particles. They're no longer the bare electrons or atoms, but they still behave as fermions. And that's absolutely crucial to their behavior. So that gives these things their pressure, for example, that they don't just collapse when you squeeze on them. And moving much further afield, if you're looking for new types of fundamental particles, your first step in proposing, say, a dark matter candidate or a new candidate for phenomenology at LHC or whatever, is probably to write down what is the particle content. Is it a fermion? Is it a boson? And then you go on to what are the symmetries. So, of course, particle statistics isn't everything, but it is very much one of the most fundamental properties that you have to describe in your theories. And it's after you specify this, It's fun because it gives rise to really radically different behaviors. So fermions exclude each other, and this is why we get the structure of the periodic table. It's what determines the conductivity of metals. And bosons, on the other hand, we said like to lump, and this is what ultimately drives phenomena like superfluidity and in some sense superconductivity as well, where the electrons pair, form something like a boson or an interacting boson, which can then condense, or phenomena like lasing. And so all of these very diverse uh, physical phenomena tie back to what are the particle statistics in a very direct way. I'm telling you things you already know, but I think it is good to appreciate just how important the particle statistics is in almost everything we do. And it's not just this fundamental distinction, it's not just because of all these phenomena, but also our whole ways of sort of understanding matter are tied to this. So this is what I was just mentioning, that all these phenomena flow from the statistics. You'll also notice an empty spot here where something else may go before too long. But it's also in things like these numerical algorithms, analytic approximations. It's only a small stretch to say that all of our understanding of matter consist of reducing some interacting complicated problem to a problem that we know how to solve, which is usually non-interacting fermions or bosons. We usually say to the undergraduates harmonic oscillators, but that's really bosons. And so just as some examples of this, you have things like Gross-Pitievsky or Hartree-Fock approximations, which I assume you've heard of, but I'm happy to talk more if not. You take an interacting, say, fermionic system, and instead you approximate it with this non-interacting H. So there's some single particle tunneling in the first term, so particles can move around. And then in the second term, there's just an external potential VI. And this VI is somehow self-consistently determined by the interactions. But again, the approach is you have a complicated system you don't know how to understand, maybe a bunch of electrons in an atom, a bunch of electrons in a solid, a bunch of nucleons in a nucleus, and you simplify it by approximating it with non-interacting fermions. Okay, so if you're interested in one-dimensional physics, another approach is to use something called the beta ansatz, which offers exact solutions to many one-dimensional interacting problems. And here the particle statistics comes in a big way. So this is a complicated expression you certainly don't need to understand, but this -1 to the p is essentially determined by the particle statistics, and it plays a dramatic role in determining the physics that comes out. It tells us what happens when I exchange two of these particles. And so if you had other types of particle statistics, it would dramatically change the structure of these beta ansatz solutions, just like it would dramatically change the nature of these Hartree solutions. And so you can imagine new tools like this. If you had a new type of particle statistics, it would give rise to new ways of understanding interacting systems. As yet another example, numerical methods. So take Monte Carlo in particular. If you know about it, there's something called determinantal quantum Monte Carlo. And it's a method that's extremely efficient for solving some very challenging quantum many-body problems. Most famously, the Hubbard model, which is related to potentially high-temperature superconductivity, or at least considered as a model of some of those phenomena, is tractable when at certain densities using determinantal quantum Monte Carlo. And the way that this numerical algorithm works is to stochastically sample a sum of results for non-interacting systems. So it has a clever way of choosing which non-interacting systems to construct, and then you take, say, hundreds of thousands or millions of samples of different non-interacting systems to get a numerically exact solution to the many-body problem. So having these sort of non-interacting particle theories of fermions and bosons actually underlies all these very different methods, and I could keep going, perturbation theory and many other things. So it's important to understand why these are the possibilities and examine other possibilities. So let's go back and ask, try to remind ourselves where this comes from in physics. So why do we only have bosons and fermions? And there are several answers to this question. But the sort of standard textbook one is to say we have a wave function, and here I'm just writing it for two particles. They have positions x1 and x2, and if I exchange those two particles, because we want these particles to be identical, that I can't tell if I've exchanged them, then I must get exactly the same wave function back, except it could be multiplied by a constant, right? So if I multiply by a phase factor, that doesn't change any physical observable. In some sense, that phase is like a hidden variable. It's something you can't directly measure, even though it's going to have consequences. So if I exchange, all that can happen is get a phase factor here by indistinguishability. But what happens if I exchange again? Well, I get another factor of this r, I'm calling r this phase factor. And now I have psi x1, x2 is r squared psi x1, x2, which tells me that r squared has to be plus or minus 1. Okay. And so this more or less is an almost airtight argument for why the only allowed particles are bosons or fermions. There are sort of famous other ways of presenting this, and I'm happy to talk more about them. Things like Linus-Myrheim connect it to the topology of three-dimensional space, and in particular, the idea that you can't distinguish exchanging twice from not exchanging at all. But it doesn't matter if you know those things. This argument is already enough to see why we have this supposed restriction, and also to see sort of start seeing where it goes wrong, where we can have more general possibilities. Okay, so the basic idea, which has a long history, is very simple. And I guess before I proceed, I did want to show you this picture. This is just a picture of one particle being exchanged and then exchanged again. So I exchanged the red with black and then black with red. And we're saying r squared equals 1 is the same as saying that double exchange is doing nothing. So the new idea is, what if this psi carried an extra index? And then R, instead of just being a phase factor, could be a matrix acting on that index. And there are lots of matrices that square to 1. Okay. And really, that's the first fundamental idea I want you to take away from today's talk. This simple textbook argument can be modified by having this index. So let me write out the math and then talk a little bit more about that. So here I have a wave function, psi, and now this new index I, think of it as a hidden variable. Just like the phase is a hidden variable that I can't measure directly, this is some mathematical artifact that you have to put in the wave function to make things work out correctly. It turns out to some extent you can actually access this information, but I think it'll help us to think about it if we imagine that it's just a hidden variable. And this shouldn't alarm you any more than having the phase of the wave function as a sort of hidden variable. So we have this index, and now I'm just writing out a matrix multiplication. There's some matrix which I'm calling capital R, that when I swap particle j with particle j plus 1, acts on the wave function psi j. Okay, so psi I is sum over j, rij, psi j. And again, you get constraints. You get the constraint that r squared is equal to 1. That's this sort of trip picture on the left that we just looked at. So if I exchange j and j plus 1 and then unexchange them, or then exchange them again, it's the same as doing nothing. And so that gives us that r squared for j plus 1 is equal to the identity matrix. Okay. And there's another constraint which comes from thinking about having more than two particles. And I just glossed over this for fermions and bosons. You also have to consider this for fermions and bosons. But you can permute these three particles in a couple different ways, and it's actually the same permutation. So if I permute the first two, and then the second two, and then the first two again, you can see it's the same permutation as doing the second two, the first two, and then the second two. And how can you see this? Well, just look at the lines, right? So red goes from bottom left to upper right. Red goes from bottom left to upper right, both sides of the equation. Black goes from middle to middle. Black goes middle to middle. Or the blue goes from bottom right to upper left. So it must not matter which order I do these permutations. It's the same permutation. But that also gives us a restriction on this matrix R, that R acting on the first two, or the R corresponding to swapping the first two, and then R swapping the second two, and then R swapping the first two, had better be the same as doing it this other way around. And this is an equation known in the mathematical literature as the Yang-Baxter equation. Okay, this is another potential point of confusion for experts, and this is that the Yang-Baxter equation is often associated with certain solutions of problems in one dimension, in particular with beta-Ansatz solutions. But that's really not what's going on here. There's nothing one-dimensional about this. You should imagine all of these exchanges as happening in 3 dimensions. Really, all this Young-Baxter equation says is that these are behaving like permutations. Put another way, they're a representation of the permutation group or symmetric group Sn. Okay, so it looks like the task at hand is all we have to do is we have to find some R's that solve these equations. And in fact, many, many, many such R's are known. We are not the first people to suggest this. This has long been pondered in quantum mechanics. And so Dirac, back in 1945, gave a public lecture where you can find this quote. This is Google translated from French, but I hope that the essence survives. It says, it was found in the experiment that all atomic particles are either fermions or bosons. It is theoretically possible to have particles which are neither, but such particles have never been observed. It is a law of nature that all particles are either bosons or fermions. So it was on his mind, but it seemed to be a settled deal, maybe based on experiment, maybe he had some other considerations as well. And right around the same time, another founder of quantum mechanics, Wolfgang Pauli, in his Nobel lecture talks about it was first shown by Heisenberg, talks about these indistinguishable particles. He says, 3 different hypotheses turned out to be logically possible concerning the actual ensemble of several like particles in nature, meaning several indistinguishable particles. The ensemble is a mixture of all symmetry classes, meaning sort of a mixture of fermions and bosons. Only the symmetrical class occurs, that's bosons, or only the anti-symmetrical class occurs, that's fermions. And then he says, as we shall see, the first assumption is never realized in nature. So it's actually not clear to me if he has exactly the same idea of attaching an index to thing, but certainly this idea of going beyond symmetric and anti-symmetric wave functions was on the mind of these pioneers of quantum mechanics. And then a little bit later, about a decade later, Green actually proposed a theory that realized paraparticles in the sense that I'm describing to you. And this theory was completely well-defined. It obeyed all the cherished principles of many-body physics that we would like a system to have, things like locality, which is going to be very important to this story, unitarity, that probability is conserved during time evolution. It was all fine. And in fact, later, Greenberg and Mazaya in 1965 said, well, maybe quarks are actually a new type of particle statistics. This was sort of, while the quark model was being developed. So they knew there were these fundamental particles inside protons and neutrons, and they were trying to figure out how they worked. And they thought maybe essentially they were thinking that the color of the up-down nature of these quarks was in fact maybe a paraparticle index. However, interestingly, all of these theories were found to be secretly equivalent to fermions and bosons. Okay. And so we had this idea, maybe there are paraparticles out there, but we don't see them in nature. And then these attempts to actually construct paraparticle theories ended up secretly being equivalent to fermions and bosons. And then in the 1970s, people thought, maybe this isn't a coincidence. Maybe they really can't be there. And so to summarize this paper far too succinctly, there's a famous set of results coming from the algebraic quantum field theorist in the 1970s, known as DHR theory, that says these are impossible. Paraparticles are impossible. Everything has to be fermions and bosons. And the key ingredient is locality. So the claim, the sort of argument that's presented in these very formidable papers, is that once you have locality, fermions and bosons are the only types of particle statistics that survive. And what do I mean by locality, or what should we mean by locality? We mean the idea that if I perturb a system at one point in space, I can't just instantaneously affect something that's far away. Nothing travels faster than the speed of light, for example. And so this idea of locality should constrain your theories, and this is a mathematically rigorous theorem. What could go wrong? And so in some sense, I think this really tampered enthusiasm for the idea of parastatistics because it looks like the case is closed. And this has made its way into textbooks. So, for example, Asher Paris has a beautiful textbook that I've only recently actually read any of, but it's a very interesting, unconventional book on quantum physics. And there's a whole section in there about parastatistics, which talks about exactly why parastatistics are impossible. So he gives an example and says that, we want to have identical particles. It will be shown that these other possibilities, meaning paraparticles, while mathematically well defined, are unlikely to be realized in nature. Bosons and fermions are the only acceptable types of particles. And you can find such statements in several books. Now, we do not, so I'm going to tell you, of course, that this is all wrong. This was, this is me uh, just coming shockingly close into my Einstein was wrong phase of my career, I guess. But we do not violate these theorems. So despite the fact that the models we have are local and not fermions or bosons, they don't actually violate these theorems. So depending on how much time I have, I actually suspect I won't have much time. The out is that these theorems actually make stronger assumptions than locality. They assume something called no remote detectability, which is just too strong of an assumption. So if we have time or if you're very curious about it, just let me know and we can talk about that. But otherwise, I just want to be aware that there are these theorems and that we are not violating any known mathematics, or at least any mathematics that I know. Also, you may say, aren't there other sorts of obstacles? So DHR is the one that I mentioned, but you might think, what about spin statistics? So spin statistics does not present an obstacle to any of this. Spin statistics actually says that if a particle is a fermion, then it has a half-integer spin. If it's a boson, it has an integer spin, but it remains silent on the issue of what could happen if it was not a fermion or boson. Okay, so spin statistics doesn't provide any obstacle. And there's also this Linus Mirheim paper that's a beautiful paper and really underpins a lot of the thinking about anyons. But really, it just says that the paraparticles or the particles must be representations of the permutation group at the end of the day, and that's going to be totally satisfied. So this is, again, just in case you want to raise other objections, these are not showstoppers here. Okay, so let me actually get in then to what we have done, because something was stopping everyone else from implementing this idea of attaching this extra index onto the particles. And the main thing that was stopping people is because they were still thinking in this first quantized way. Thinking about locality is difficult in first quantization. In first quantization, you have a wave function. It's a function of all the coordinates, but that's just it. The wave function depends on all the coordinates, no matter how distant these particles are away from each other. If you have something that's like a second quantization, which I'll just review and show you here, then it's a lot easier to think about. And so what we would like to see is that when two events are separated by more than the light cone, so when they're space-like separated, then they should really not be able to influence each other. Information should not be able to propagate faster than the light cone and things like this. And so there's a fundamental result proved by Lieb Robinson that if you have a Hamiltonian that's a sum of operators AR, and each of these operators is localized around the point R, so I'm thinking of R as some spatial location, then and these ARs commute when they're far away, then there's a finite speed of information propagation and locality is fine. Um, and this also implies it's equivalent to saying that a perturbation cannot instantaneously affect a faraway region. Okay, and so this is nice in second quantization because what you do is you say your allowed operators are things like f dagger f, and these automatically commute with f dagger f on two different spatial points that are far away, and that guarantees locality. So what we need to do is figure out how can we think about paraparticles in a second quantized way and ensure that we look at observables that commute like this. And once you have this, then you have locality and quantum mechanics holds, so you're very happy you have a candidate theory for particles. Okay. That's kind of the background, and now I'm going to actually show some equations and tell you how this works. Maybe I'll pause just in case there are questions yet, because I would rather, not get ahead of my skis here.
Don't think there are any questions at the moment. I think everyone is too riveted.
Excellent. Well, if you change your mind, feel free to type something in. Um, okay, so here is where I will start writing some equations, which can look rather scary, but I hope you don't have to pay too much attention to where all of the indices go to make sense of this. So in usual second quantization, you have some creation and annihilation operators, psi dagger and psi. Here I'm using psi plus and psi minus because in the most general case, these are not Hermitian conjugates of each other, unlike the familiar case. But actually, in all the models I really care about, they're Hermitian conjugates of each other. So if you want to just think about these as like psi dagger and psi, instead of psi plus and psi minus, I'm fine with that. And these operators have two indices. They have one index that is just a mode index. So this is like you create a particle at position R or at momentum K. That's what A would represent. They also have the second index. This is just like what you'd have if you had a particle that had spin. So you could have a spin sigma, and you'd be creating a particle in mode A with spin I. So I'm calling it I here. But it's not spin. It's something that's analogous to this hidden index that I was telling you about before. And in our normal second quantization approach, we would have psi dagger AI, psi dagger BJ is just equal to plus or minus psi dagger BJ, psi dagger AI. And based on what I told you about the first quantization, it's maybe not all that shocking that you can upgrade this to something with more general statistics by having a matrix act on these parastatistical indices or these hidden indices instead of just getting a plus or minus one. So I've essentially replaced that phase factor with now a matrix that acts on those paraparticle indices. So it's a little annoying to always have to write this stuff, but conceptually, hopefully it's not too bad. Now, it turns out if you want to have all the nice properties of a theory that you might, so for locality is going to be a big one, but also you'd like it to be solvable. If you have Hamiltonian that's quadratic in these sorts of variables, you'd like to solve it. Certainly you can for fermions and bosons. So if you want to have all of those types of properties, you also have to be careful about the commutation relationships for minus minus and plus minus. And a little work will show you that they all look essentially identical, but the indices go in different places. And again, you don't have to know anything about where those go. I'm just pointing out that that's everything. So if you understand these commutation relationships, then you are capable of working with a fermion, with a paraparticle theory, and you work with it very much like you would a fermion or boson theory. You want to normal order things, and you can do that using the commutation relationships, for example. However, just like earlier, we talked about how these matrices had to square to 1, and they also had this Young-Baxter constraint. Those were the pictures I showed you on the right. That implies something about these tensors R. Notice it's a 4-index tensor because there are 2 para indices on the right, 2 on the left. And so graphically, I'm representing these tensors. This equation on the left is telling me that R squared is equal to the identity matrix. Okay, and so I'm using a pretty standard tensor graphical notation where tensor with 4 indices is drawn as some geometric object. Here a square, and each corner of that square carries one of those indices. And if I draw a line connecting 2 of those piece of corners together or just smush them together like I have here, I'm supposed to contract that index. So again, the details don't really matter, but just to be precise about what I'm presenting here. So this left one says R squared is equal to 1, or if I exchange twice, I get the same thing back. And the equation on the right is just the same thing as this graphical drawing I did earlier, saying that these 2 different ways of permuting these 3 particles had better give the same result back. So now you have to go solve these 4-index tensor equations. And if you can do that, if you can find solutions, then you use these commutation relationships, and it turns out that you have exactly the type of particle you've been looking for. And it does turn out, as we showed and as is known from other contexts, that there are solutions to these equations. So there's another important ingredient. Remember, to get locality, I actually have to tell you something about what I'm allowed to write down for Hamiltonians or measurement, observables that I could measure. And the point is that this works just like usual for fermions and bosons with one small change. So for fermions, I could write something like psi dagger psi plus the Hermitian conjugate if necessary. And I can do the same thing here, except I have to contract over the paraparticle index. And that's really the only difference. So if I had a spin here, if this I was a sigma, I wouldn't necessarily have to contract that index. But with these paraparticle indices, I do have to contract it. And then after some algebra, the point is that you can show that operators like this commute with operators that are far away. And then by what I alluded to earlier with these Lieb-Robinson bounds, this guarantees locality. Okay. So at a formal level now, in principle, I could end the talk. You could go home and you could start solving paraparticle theories yourself. And I'll show you some examples of this and some of the things that come out. But that's really the rules of the game. And so just to recap, the ingredients are that we modify the second quantization commutation relationships. Any observables, which are things you can measure or which appear in the Hamiltonian, have to be contracted in the paraparticle index. And then once you do that, these observables at different points in space commute, so you get locality. All right. So this is all a little abstract, so I want to give you a more concrete picture of telling you what that R matrix is actually doing. So here is an example of exchanging two particles. And I'm drawing it as a spin, but this is the parastatistical index just represented in a way that I think we're used to thinking about. So my particle on the left here exchanges with the particle on the right. Initially, my left particle is up and my right particle is down. So if these are ordinary fermions or bosons, the spin just follows the particle. So my upspin on the left goes to an upspin on the right. My downspin on the right goes to a downspin on the left. And what changes with paraparticles is that you can have other things happen when they exchange. So you can have this upspin and downspin actually rotate to some new spin state. Rotate to some new spin state when I swap the two spins. And the R matrix, the R tensors that I showed you, specify exactly how that happens. Okay. And so this may or may not sound like a big deal, but the point is that this happens no matter how far apart these particles are away from each other. I could have one particle on the Earth, one on the moon, and as the moon orbits around the Earth and they exchange, they would do this funny spin rotation. And so that's pretty weird, and you can start to see maybe why it's hard to make this agree with locality. But my claim, and what I've argued that if you go through and calculate some commutators, you'll see, is that with the prescription I just showed you, you do in fact get this kind of behavior, and yet despite it almost being non-local, looking non-local in this sort of picture, there's no way to use this to say signal faster than the speed of light. And then I really like this picture that graphics artist Mario Norton here made for us. This is just a sort of conceptualization of this, but it helps you remember that this is not a 1D thing, unlike my drawings. This is really happening in 3 dimensions. And so if I have a yellow particle here and a red particle here, and then you think about moving up, this is like exchanging places, that they evolve into some new colors after doing the exchange. And the way they change colors from yellow to red into green and purple is specified by that R matrix.
So Kadan, sorry to interrupt, in that simple little diagram you've got there, it's then implicit, is it, that a second exchange, does that come back to the original two states?
Absolutely.
Or do we get
Potentially
back
up to a plus or minus sign.
Yeah, okay, all right.
Oh, sorry. If you sorry. If you do it twice, if you exchange twice, you go back to the original state. Yeah.
Okay.
But I should say, if you do it once, you could also have a plus or minus sign in front of this.
And that automatically comes from the for the equations that you had on the previous slide.
That's exactly right. It's directly tied to this left equation here.
Yeah, I see. Okay.
R tells the spins what to do when you flip them once. And in fact, that's what this middle equation is saying. It's literally saying that that's what the indices do. And so that's exactly it. Yep.
Right. Thanks. Sorry to interrupt. Just want to clarify.
No, be my guest. And so that's certainly not the only possibility. This is just an illustration. There are many different R matrix solutions to this, and each of them gives a different type of paraparticles. Okay. Now, at this stage, mathematically, it certainly looks like there's something distinct, but you could ask yourself, how can I tell that these are really different than fermions or bosons? And there's kind of an abstract way of seeing this, which is that when you exchange them, you get this behavior. This behavior, it turns out, is sort of topological, so there's no way to deform it to fermions. But the issue is, I said these spins or these para indices were kind of supposed to be hidden. So we could have a long, subtle conversation, or I can just give you a more direct way of seeing this. And the more direct way to see this is, instead of thinking about the exchange statistics, we're going to think about the exclusion statistics. And so how can we get the exclusion statistics for this? And I'm just going to take an example of an R matrix that's given here. And again, you don't need to read this equation, but if you want to verify the next couple equations that I'm going to give you, that's where it comes from. So it's a very simple R matrix. If you think about the vacuum, it turns out there's always still a unique vacuum state. If you have one particle, the one particle state space is just like it would always be for fermions and bosons. There's no distinction. So the first distinctions that happen when you try to put two particles in the system, and in particular, two particles in the same mode, say at the same lattice site or same momentum state. And so I'm just going to suppress the position index or whatever and just look at the para indices. So we just have one mode, and I want to know what happens when I put two particles in it. So here is sort of what happens in the two particle state space. I get it by acting on the vacuum with psi dagger, psi dagger. And actually, I did not suppress the mode index. I should have to make it simpler, but just ignore the A, B indices for now. So the this was the equation I had before in the sort of defining relationship. I just plug in this value of R that I put up on the left here. And this equation tells me that when I swap the modes A and B, but I don't swap the spins, I get a minus sign. So this is the difference with fermions. Fermions would also swap the spins in this equation, but here I'm not swapping the spins. That's what this simple R matrix does. And you can see pretty quickly by picking A equal B here that this tells me psi dagger AI, psi dagger AJ is equal to 0. In other words, I can't actually put two particles in the same mode for this type of paraparticle. So this is different from either non-interacting fermions or non-interacting bosons because I have an index. It's like a spin. So think about a spin 1/2 particle. That would be like if this index took two values. I can have spin up, I can have spin down, but I still can't put two particles on the same site. So this is like a model of what we'd call hardcore fermions, spin 1/2 fermions. And in general, these R matrices often give you generalized exclusion statistics, just like I'm illustrating here. You can go plot things. This is just the analog of the Bose or Fermi function, but plotted for some different R matrices. So bosons are this dashed line at the top, the red orangish one. Fermions are this blue one. They're being plotted as a function of the energy over temperature. And then the other two dashed lines in the middle are just two different types of paraparticles. Okay, so you get this generalized exclusion, and it's then one line of algebra just to see that there's no way that you can write these sorts of mode occupations in terms of any system of fermions or bosons. Okay, so that's the basic theory. The question is, where do we actually look for these things? So just because I've shown you a mathematical theory, it's got all these operators, it looks like a second quantized thing. You could write down field theories to your heart's content to look for these. But unless nature just gives us a paraparticle, what are we going to do? Right? Where do we look for these? So maybe it turns out, tomorrow LHC turns on and sees a paraparticle, and I'll be very excited, but I certainly am not holding my breath for that. So where else can we look? And going back to the start of this talk, remember I motivated particle statistics by all of the effects that they have as quasi-particles on the world around us. And here it turns out that the simplest case can be realized in ultracold molecule and Rydberg atoms. And in fact, it has basically been realized or is actively being realized as we speak. And so I'm going to talk about this, but it's also because the model that gives rise to this can just give you a concrete example of how excitations in a system can look like something that's not just fermions or bosons. So as a warm-up, I'm going to review a different case where you have a spin model, which is in some sense a bosonic model because a spin doesn't move around. You can have down or up, which looks like 0 or 1 boson occupation, but creating a spin on the right and on the left commutes with doing it the other way around, just like things commute for bosons. So in some sense, spin models are bosonic, and yet you can have spin models that have emergent fermion excitations. So the simplest example of this is a nearest neighbor XY model. So the Hamiltonian is just sigma plus, sigma minus, plus the Hermitian conjugate on nearest neighbors. It just flip-flops spin 1/2. And a long time ago, Jordan and Wigner showed that you could actually map a Hamiltonian like that to a system of non-interacting fermions. So you start with an interacting spin model, which naively looks very complicated to solve. And by doing this transformation, you get something that's non-interacting fermions. And the form of this transformation is non-local. It looks like this equation that I've got here. So intuitively, the F dagger, creating a fermion on site I, corresponds to flipping a spin on site I, the raising a spin on site I. And this, it goes back to the intuition. Spin down is like the vacuum on that site. Spin up is like having one particle on that site. But because we have these weird anti-commutation rules, we have to attach a string to the Fi. So for all the particles to the left of site I just count up how many particles there were to the left and put -1 to the number of particles there. And that ensures that I get the right commutation relationships. What does this mean physically? So physically, it's the domain walls that are acting as the fermions. So you can rewrite the sigma plus, sigma minus as an XY model. I'm just going quickly in case you've seen this before, but the fermion operator, if I invert the equation I had before, now looks like, remember it was like a sigma plus, and then this string of all the upspins, -1 to the number of upspins to its left. To think about it, for me at least, it's easier to think about it in a rotated basis. So I'm just rotating XYZ to YZX. And then I get that F dagger is some stuff on, so F dagger on site I is some spin stuff on site I, and then a string of these sigma X operators. Okay, things involving sigma X operators. And what does sigma X do? It flips a spin. And so in this rotated basis, our ground state is just a ground state is just a fully magnetized state. All the spins point down. And when you act with this fermion creation operator, it creates a domain wall that looks something like this. So all the spins to the left point up, and then on site I, there's some rotated weird spin, and then everything's left unaffected to the right. So physically, these fermions aren't just abstract mathematical mapping, but they really correspond to these fairly intuitive things, which are the fundamental excitations of the system, these domain walls. So on the left, it looks like one of the ground states. On the right, it looks like one of the ground states. And then there's some funky spin maybe in the middle connecting them. Okay. So that's the math and the physical picture of how you can map spin excitations to fermions. But here, oh, and here, if I have lots of fermionic excitations, and this is what's really remarkable in my opinion, is that they don't just form some complicated interacting fermion system, but it forms an ideal gas. These are non-interacting fermions. So although the objects are kind of complicated, they're these domain walls, they don't interact with each other. But they do acquire this fermionic minus sign. So maybe, as you'd guess from the story I'm telling today, the story for paraparticles is very similar. So you can write down families of Hamiltonians in one dimension that have exactly a similar structure on nearest neighbors. They have some spin-spin interaction. Don't worry about this. I'll show you an example in a second. In general, they're extremely complicated. Um, and these will map by some transformation to a non-interacting paraparticle system. And these paraparticle excitations correspond to domain walls in the spin system. In the new insight, people have actually tried to solve spin models, spin one models, and things using Jordan Wigner in the past, but it's never really succeeded precisely because everyone's been looking for mappings to non-interacting fermions and bosons, I think in some sense is the way to say it. And you also need a new type of Jordan-Wigner mapping. So if you remember before we had this product where you took some product of all the minus one of the sigma z or product of sigma z's on all the sites. Here we have something called a matrix product operator. And I don't want to get into the details of this. It's very common for people who do numerical work in tensor networks. But despite the fact it's got a scary graphical symbol, it's pretty easy to work with, or it's pretty possible to work with. These are just a generalization. Instead of having a product, it's now a product of, say, 2 by 2 or 3 by 3 matrices that you can work with. Okay. And again, once you do this, you have an exact solution. You can calculate whatever you want, and there's a direct physical interpretation in terms of domain walls. Okay. But I want to get a little less abstract with this and give you a concrete example as well as connect to actual experiments. So now I have to take a step back and tell you about experiments. How can you realize spin models in experiment? And you could go look at your favorite material and look for one-dimensional materials. We're thinking a little bit about that. But where something I'm very familiar with is ultracold molecules that are in optical lattices or optical tweezer arrays. So you can think about this is there's now a large community of people who are making these systems. They cool molecules, peculiar molecules like potassium rubidium molecules, for example, down to nanokelvin type temperatures where they can be held in place by these optical potentials. And after they do this, then they're just frozen in these traps, at least in some of these experiments. But the particles can still interact with each other. So molecules can rotate, for example. And the actual rotational spectrum of a molecule is complicated, but it doesn't matter for us. We can pick 3 of those rotational states. I'm just calling them n-1, n, and n+1 here. Hold them in their individual traps and let them interact with each other. So what does that interaction look like? Well, you remember going back to your E&M class that molecules are dipoles, well described by dipoles, and that the dipole-dipole interaction is d dot d, that's the product of the dipole moments of the 2 molecules, times some 1 over r cubed that characterizes the decay in space, and then some anisotropy factor 1 minus 3 cosquared theta. You actually don't have to worry about any of this except for the d dot d part. That's all I'm going to care about. If you also remember your quantum mechanics selection rules, when you have a dipole operator, it's a vector operator. It can only change the angular momentum by plus or minus 1. And so if I have these molecule rotational states as a sort of ladder of different angular momentum states, then I can go up or down this ladder for particle 1, for molecule 1, by plus or minus 1, and same on the right. So I can have processes like I drew here, this kind of flip-flop where n+1 goes to n+1n, or I could have n-1n goes to n-1, but I can't have, it turns out, these other processes. They'd be allowed by the matrix elements. I could have the middle goes to the outer 2, right? Or I could have both go down. Those both satisfy selection rules. But it turns out these are far off resonant in energy. So these are not equally spaced levels, and so these terms turn off. The only terms that are allowed are these flip-flop terms. So if I do this with 3 molecular rotational states, and I allow this kind of native interaction, I get some spin model that I could write down explicitly, but it's easier just to think about as having these flip-flop terms. Notice if I only add 2 levels, this is exactly the spin 1/2 xy model that we just talked about. And all I'm doing is adding a 3rd level to it. And this model is exactly solvable. You can see this has become something of a hot field with molecules as well as with Rydberg atoms, and there are some reviews that might be useful that I put up on the screen there. So this is an illustration putting it into the context of paraparticles. So you take a one-dimensional chain of molecules in these traps. These molecules cannot move around, but they can interact by this flip-flop. And you should think about the middle state as being something like a vacuum state. The top state is something like having a particle on that site with a spin up. And the bottom state is like having a particle with spin down. That's the analogy we're making when we want to think about these as particles. And then after you do a generalized Jordan-Wigner mapping of this model, it maps to non-interacting paraparticles. And these are non-interacting paraparticles of precisely this simple type that I showed you the exclusion statistics of earlier with this R matrix up here. So they're hardcore fermions, and that's the simplest type of paraparticle. And so you might say, people have looked at hardcore fermions before, but these have never been exactly solvable, and it's never been appreciated that their statistics is actually this sort of exotic thing. Of course, it becomes more pronounced in higher dimensions, but still, it would be very interesting to observe this. So the experiments by Bryce Gadway are sort of ongoing at Penn State. He's just getting started. He's done a lot of other experiments in this system, actually using a lot more than 3 levels and what are called synthetic dimensions. We've collaborated a lot on this. But he's not using molecules. He's using Rydberg atoms and using different electronic states of Rydberg atoms. These are just really highly excited atoms, but really highly excited atoms are also dipoles. And so the physics is almost identical. And so in some sense, I think they're probably kind of sitting there in his experiments already, but we need to figure out what are the smoking gun signatures that really highlight that they're seeing parastatistics. And one thing they can do is measure the equation of state, which gives sort of direct insight into the exclusion statistics that I showed you. The other, even more ambitious thing, but I think very doable, is that you can prepare the single paraparticle excitations. So that's these domain walls, and scatter 2 of them off of each other. And by looking at what happens to the spin as they scatter, or to the para index as they scatter off of each other, you can directly probe that exchange. So that's in 1 dimension. I do want to mention that we have exactly solvable models in 2 dimensions as well. And there's no way I'm going to be able to explain this model to you. This would be probably a seminar in its own right. This is a generalization of what's called a quantum double model, which is in turn a generalization of what's called a toric code model. The graphics on the left are the model. The Hamiltonian is a sum of terms where each term is one of these symbols, and these symbols are all these matrix product operators that I had mentioned before, and one of them is an 8-body matrix product operator. So these are very experimentally unrealistic models, but they're completely physical in the sense that they're local spin models that in principle you can write down and solve. But it's nice because despite all of the complexity, it's exactly solvable, and we can see it has paraparticle excitations. We can see if we tune the tunneling matrix or the spin-spin interactions in the right way, that you can actually get new chiral topological phases that lie outside the existing classification of these. This is also, to my knowledge, the first solvable model of anions in 2 dimensions. So because this is 2-dimensional, you can consider this particular case as a special class of anions. But nobody's ever had a solvable model with mobile anions before. And so I think that that's something that's just a new theoretical tool for us to play with. Okay, so more or less that's the tour of paraparticles. This is just saying it's a generalization of the toric code. And if you recognize that picture, that's the toric code. If not, that's fine. So where I think going with this is that beyond 2 dimensions, we would like to be able to find these. And here I mentioned you could do this on a quantum computer, which you could, but again, how interesting is that? You tell me. I'll talk to people and try and see if they're interested in doing it. But where we really want to go is 3D. And in order to do this, we need to find ways of not just dealing with these sort of exactly solvable toy problems, but being able to take a realistic spin model and whether through approximation methods or numerical methods, actually see if it has paraparticles. And so there are analogs of quantum Monte Carlo, parton constructions that we can use and we're starting to work on. So I think I'm just going to conclude here with talking about the sort of implications beyond the sort of headline result that, okay, you have new particles, but who cares? So remember, I started the talk by saying fermions give rise to all of these characteristic phenomena: magnetism, periodic table, metallic conductivity. Bosons give rise to lasers, superfluidity, and vibrations. Now we have the same thing. We have a new type of particle. We know it can arise as emergent quasi-particles in sort of condensed matter in principle. But we actually have no idea what phenomena it gives rise to. We're at the stage that we have studied the non-interacting theories. And similarly, earlier we said that all of these numerical methods for treating interacting systems rely on the particle statistics. We were able to do Hartree-Fock or beta ansatz or deterministal quantum Monte Carlo, often by mapping to non-interacting particles, sampling them, or whatever. And now we have a whole new class of methods that you might be able to take some previously unsolvable model, map it to paraparticles, and then use Hartree-Fock or DQMC on the paraparticles, the analogs of these methods for paraparticles, to gain a window into totally new phases. And it's a little daunting how much is ahead of us, I think. And this is where, if you are sitting on your thumbs and thinking about what should I be working on next, this is my advertisement that there's a lot of work that I think is very exciting to do, which is basically any question that you could ask for fermions or bosons, you can also ask for paraparticles. And I see David coming on. This is my last slide, so if you're going to kick me off, that's why. And let's just start in one dimension. Did you have a question then, David, or
No, sorry.
okay.
I was
Just
just
checking. Okay. So in one dimension, what happens when I turn interactions onto fermions? Well, sort of universally, in many cases, I go from a Fermi gas to a Lettinger liquid at low energy. What happens for paraparticles with interactions? No idea. Okay. But I think you can make progress using very similar arguments to what has been done there. What happens to bosons or fermions with contact interactions? Well, you can use beta ansatz to solve this, and you get a Lieb-Liniger or a Yang-Gaudan gas, and you can understand all of their sort of equilibrium thermodynamics, and with generalized hydrodynamics, we're starting to understand their dynamic properties. What about paraparticles? No idea, right? But again, I think you can actually develop a beta ansatz for interacting paraparticles. What if you had a tunneling barrier in a Fermi gas? So it turns out that you get a complete reflection. This is a famous result by Kane-Fisher, and there's actually some subtleties and discussion about this, but that was the Kane-Fisher result. Things like orthogonality, catastrophe, what happens with paraparticles? I don't know. Okay, so that's kind of the theme here. I keep not knowing, but we should find out. What about D greater than 1? Well, Fermi gases become Fermi liquids, and then you have this phenomenal subject of Fermi liquid theory. Um, is there a paraliquid theory? I think there should be some analog of it, and we should develop it. We know when you add attractive interactions, you have an instability to superconductivity. Do we have instabilities of paraparticles, and are they interesting? With strong repulsive interactions, you can have instabilities to magnetism and nematicity and other things. What happens with paraparticles? So I don't know. I'm just saying these are all, I think, great research projects that we're starting to think about, and I know other people are starting to think about as well. Intriguingly, the paraparticle liquid, so even the paraparticle gas without interactions, may be a type of non-trivial Fermi liquid, what's called an FL star phase. It, in fact, behaves very much like a Fermi liquid, but it violates Lettinger's theorem, which relates the Fermi volume to the number of particles. And this is due essentially to the generalized exclusion. So I don't understand this very well. Put this as a tentative, I'm trying to understand what all this means, but I think this may be a solvable model of this so-called FL star phase. All right, so let me just conclude here. For a long time, people have contemplated paraparticles, but thought they were impossible. However, in this recent work, we now know that they are possible and even consistent with these ideas of locality. They can be both fundamental. In principle, you could have a fundamental particle that's a paraparticle, or at least if you can't, we don't know why. There's no principle we know of that rules them out. And they can also be emergent. And I showed you some 1D and 2D spin models where that was the case. And then they have all these implications of giving us new phenomena and may provide new tools for understanding correlated matter. And hopefully in the next 6 months or year, we'll have a first observation in these simple 1D cases of some type of paraparticles. So thanks for listening, and I'm happy to take any questions.
Thanks. That was a really, really good talk. What I found, there's no other, I don't think there's any questions queued up just yet. So that gives me license to ask a couple.
Sure.
Um, so I mean, this is so elegant, and you made it sound so natural that the first thing you ask is, how come there's an entire class of particles in the, in our ordinary experience of physics that
Mhm.
have these properties? Have you got any ideas as to why nature might suppress? I mean, they exist in these special cases that you've talked about, and the fact that you can immediately relate this to potential experiment is really nice.
Mhm.
But I'm wondering, do you have any insight as to why nature would say, yeah, well, that's all very fine, Caden, but I still like fermions and bosons?
Um, so I'll answer that question in a second. Let me start by saying that I think they could be hiding under our noses, just like I think that maybe there are materials with topological phases that were hiding under our noses and we didn't know what to look for. And so if you don't know what you're looking for, you just go, here's some complicated thing I don't understand. But it turns out it's actually some beautiful, simple function describes all this, whatever. Um,
Right.
so so maybe, in fact, they're already out there. And maybe not, but maybe we have to engineer them and why they don't just naturally occur, I wouldn't really know. Let me give some scenarios where there could be new undiscovered principles which forbid these. Okay. So again, none of the principles of physics I know actually forbid these, but there are, possible new principles that could. So, or maybe possible pieces of physics that could. So the paraparticle liquid, maybe all of these theories are perfectly well-defined Hamiltonians, but maybe they're all unstable. So any perturbation you add, they just, you know, decompose. And I don't think this is a legitimate possibility. I mean, it could be in the true ground state that that's in fact what happens, but as long as you're at a temperature scale that's not too low, that really can't happen. So you can do a high temperature series expansion around the non-interacting point, and as long as you're at a temperature that's kind of large compared to the interactions, you just won't see the interactions, and you should still see something that looks like non-interacting paraparticles. But in terms of a true ground state, they could be unstable, and so maybe that's part of it. Another thing is these models we have are awfully complicated. Maybe there's some hidden principle we don't understand that requires that requires them to be complicated. Maybe you have to have strong eight-body interactions to get paraparticles. I don't believe this. I don't know any reason it should be the case, but I don't have direct counter evidence. I do think if there's something like that, it's probably pretty interesting because we've discovered a sort of new principle that's restricting the types of things
Exactly.
that are allowed. So,
Yeah, exactly. That's right. No, that's what's so interesting. Yeah, any new deep fundamental principle like that it would arise out of this would itself be very interesting and potentially far-reaching.
yeah,
The other
exactly.
question that I wanted to ask you about was, can you say a little bit more about, you said this was consistent with locality, these
Yep.
solutions. Can you just say a little bit more about that? I mean, in the case of the Lieb-Robinson bound that you alluded to, you can extend that beyond lattice models into continuous models. But if you're just talking about a lattice model for the moment, I'm trying to think back. It's a while since I've read
Mhm.
since I've read this. But my understanding, correct me if I'm wrong, my understanding is that the exponential decay nature of the locality, the bound, that particular functional form enters into the Lieb-Robinson bound probably because of the exponential functional form in the time evolution operator, I think. If you do,
Yes,
it
although
goes through
it's
the,
not quite direct, but at the end of the day, these are closely tied together. Yeah.
yeah, okay. So now how would that generalize to the case of paraparticles,
So in the case
do
of
you think?
paraparticles, as long as you have a model where you have a sum of these bilinears as the terms in your Hamiltonian, and these bilinears then commute with each other, they also have an exponential decay of correlations outside of the light cone. So in fact, it's identical to any of these other models. Yeah.
Okay. And that's the origin of the consistency with locality for these.
Um, that's exactly how you can see these are consistent with locality. That's right. And in fact, we had this. I mean, back in Jiwan discovered these back in 2021. He was bored during COVID, and as one does when you're bored, you start playing with representations of the Young-Baxter equation. And so,
Naturally, yeah, of course.
exactly. And then he um, uh, he sort of came up with this, and we saw it was local, but we assumed we had to be missing something because of these theorems.
Yeah.
Because I still haven't told you how it actually evades the theorem. I've argued that it's local, but I haven't
Yeah.
told you what's wrong with the theorem.
Yeah.
So here's what you can go. It's in like the first paragraph of the theorem. They're sort of in human words before they get deep into the algebraic quantum field theory. They're describing the assumptions of their theorem. And they actually assume something stronger than locality. They assume no remote detectability.
Yeah.
And what I mean by this is that I can't do measurements far away, infinitely far away, and detect that there was a particle there. But if you think for a moment, actually, this is too strong of a requirement. If I have an electric charge and I build a detector at infinity, Gauss's law tells you just add up the electric field everywhere.
Yeah.
And this doesn't violate locality in any way because it would take time to build the detector, so there's enough time for information to signal or to correlate
Yeah.
signal from across the detector or something. So you should allow remotely detectable particles, and in fact, anyons are remotely detectable. So if you believe the whole anion business, you should have no problem with remote detectability. Um, and so, yes, paraparticles are remotely detectable, but I think this is no more dangerous than having a charge or having an anion. The DHR is a very profound theorem, but it's more restrictive than maybe people have assumed. There are also some other ways they've maybe overinterpreted the theorem, but in my mind, that's the most interesting.
Right. That's interesting. And 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 when you were generalizing your model, you could
Mhm.
also talk about things like quantum entanglement growth that would follow naturally,
Yep.
also probably. Yeah.
Absolutely. And I didn't talk
Yeah.
about it, but Jiwan actually has a nice paper following up on this, showing how if you exchange two particles, so you
Yeah.
start with a paraparticle in the corner of the universe and one in the other corner of the universe, and you exchange them, you can actually use that to communicate between two particles that never touch each other, which on its own is not so striking because one person could just leave a note and the other person could come pick up the note. But it turns out there's absolutely no way for any eavesdropper to read the message, unlike a note. So they can't even tell that you've left a note. And so there's this way to
Okay.
secretly communicate. You can also, I think, we haven't worked out the details, but in some sense, this R exchange is applying a quantum gate to the parastatistical index. So to the extent that you can access that parastatistical index, you can actually do a sort of topologically protected quantum gate. Um,
Oh, beautiful. Okay, that's really interesting. Let me
mm.
see if there's any. I don't think. Oh, yes, there's a couple of questions in the Q&A. Zimin Lee, my colleague from ANU, wants to know, are there any potential interesting generalizations of spin boson model by including paraparticles?
Yeah, I think that's a really interesting question. So, in part because I think it'd give you some interesting physics, and in part because, in some sense, spin boson models can be a little bit simpler than just tackling a general complicated many-body model. And there are a couple different obvious generalizations that come to mind off the top of my head. One would be you replace the spin with a paraparticle somehow. But probably the more realistic one, or the one that's a little clearer what it would mean, would be you keep an ordinary spin and you replace the bosons with paraparticles.
Okay.
And so, if nothing else, to the extent that having that solvable paraparticle model helps you solve this problem, this could just give you a new sort of exact model for understanding uh, coupling to baths. And this gives you a type of bath that you've never had before. And maybe this even might have some relevant properties. The bath might have some relevant properties for real materials. Maybe it's non-Markovian in an interesting way, or maybe it has some other property. Yeah, I think it's a very interesting question. You could, maybe I should add that next to my list on the table here. So
Of
physics
interesting things
in
to
rear
work on.
dimension. Yeah, yeah. Spin plus baths. Yeah.
And then the next comment was interesting to see the relation to the R matrices in integrability. Do you have any rules for restricting your R matrices?
Yeah. So here, let me just flip back. So, oh, I stopped sharing my screen, but I'll fix it in just a second.
Yep, no worries.
Um, so the only restrictions on our R matrices are the following equations. Can you see this? It's not full screen, but I think that's okay.
Yeah, that's fine. It's coming up.
Okay. So this equation right here is the only equation. And so, well, there are two of them. One is this kind of R squared equals the identity equation.
Right.
Of course, this is a tensor equation, right? So they have all these indices. And then the other is this two ways of exchanging equation, the Yang-Baxter equation. But once you have solutions to that, then you're happy. And there are many solutions that are known. And even for a qubit system, like for two-level systems, I think they're completely classified into four families. I do want to make one comment, since you're asked about integrability and things. Um, the other place that these sort of Yang-Baxter type equations come up is in 1D systems. But there is a strong difference here because in the 1D physics, the R matrices are actually parametrized by, say, a momentum or something like that. Here, these R matrices are just constants. I mean, they're tensors, but they don't depend on it, something like momentum. And that actually makes these equations, I think, much simpler to deal with. So in some sense, these are simpler R matrix equations. It's just sort of the formalism that they go into is a little unfamiliar.
That's great. Thank you. I think that's all the questions for now. Thank you very much, Kadan. Once again,
No,
let me
my
remind
pleasure.
everybody, please, that there's so much great material here. If you want to watch the talk again, it'll be on YouTube within a few days, as soon as we get all of the logistics sorted. So you'll be able to watch it there again. And let me thank you once again, Kadan. It was a really, very
Yeah,
interesting.
thanks for having me. I had a lot of fun.